Yeah, hello, physics students. This lecture is on chapter 24, part 1. I'm going to call this Huygens principle and the interference of light. There's a number of properties when we started this discussion that we are going to look at and then see, if light, kind of behaves this way. And, that's kind of the idea, is just going to go detail by detail by detail here. And so I think when we really kind of started this here, we kind of looked at this idea of wave properties. And waves will bounce off of some objects, and so we call that reflection. And we have seen that we certainly get light waves reflecting off of even transparent materials. Some of the energy reflects off some, if it's transparent, so will transmit through into that material. But if you have something like like a mirrored surface, then you certainly get reflection. And we have spent considerable time looking at the idea that waves will change their speed possibly when they go into a new material. And when they change their speed, because they're following the path of least time, many times they will change their direction as well. And we call that refraction. And so then we have the law of refraction, also known as Snell's law. And so we actually use that to come up with rules of thumb for something like lenses. And so we spent some time looking at lenses, and we also spent some time looking at spherical mirrors. Okay, so when it comes to wave properties, I think we also mentioned that waves, if you have two waves in the same space at the same time, there's this property called interference. And so we're going to take a look at that today. Maybe we also mentioned that light or waves in general have this property called diffraction. I think we'll look at that in part 2. Waves can disperse, so we'll see what that means, probably in part 2 as well. And waves can also be polarized, and we'll see what that means as well. So most likely, these 3 topics are going to probably show up here in lecture number 2. We'll take a look at single slit diffraction, the idea of dispersion, and Brewster's law with polarization. They could be polarized. So, really what we've done so far is kind of taking a look at, reflection and refraction. Those properties really showed up in detail in chapter 23, and now in chapter 24, we're going to start looking at, some of these other properties here. And then eventually use some of these properties to talk about optical instruments. Some that we've already looked at, lenses and mirrors, and we'll turn that into maybe something like telescopes, binoculars, and things like that in chapter 25. Okay, let me remind you, some of you forgot this on the quiz here not too long ago, that the wave equation really tells us there are just a very few things we have to pay attention to when it comes to waves. So the distance a wave travels is what we call the wavelength. And then for us, they're harmonic waves. They just keep doing the same thing over and over and over again. So all the information is really just in one cycle. And the rate that it moves, what we call the velocity, and the time for it to complete itself one time is the period. And so, this can be written with the period taken out and 1 over the frequency is the same information as what you've got in the period. So you've got this wave equation, and what it really tells you here is that there are just a few things to really kind of pay attention to. And, one of those things happens to be the frequency or the period, because they share really the same information. So the frequency is really dependent on the source of the wave only, right? And that's all it really depends on. So if you comb your hair, I mean, I wouldn't know. I don't ever do that, but I put my fingers in my hair when I get out of the shower, and that's about it. But if you comb your hair, sometimes you can get some static cling on like the comb or the brush, and so you got charged particles on there. Now, if you wave your hand around, you are accelerating those charged particles. They're giving off waves, okay, and they're giving off a wave that is precisely the same frequency as the source. And the source really is your hand. So if you move your hand back and forth 1 time a second, then the frequency of the wave is 1 time a second. So the wave that they're giving off has a frequency of 1 hertz. Okay, and so this is going to be a radio wave. This is going to be a very, very long wave, and your eye is not going to see this wave here at all. You've got to wave your hand probably up and down, something on the order of billions of times a second to be able to create a wave that we can see here. And so maybe we had a quiz question where a radio station was chasing electrons up and down a pole at a certain rate. Well, that is exactly the rate that they're pushing the charged particles. That's the source then of the wave, and so then the wave has exactly that same frequency. So that's just a product of how waves are created, and it's just something that we have to really kind of pay attention to. So the second important idea that we see here in the wave equation, so we kind of have something there that we can say with definitive results, that the frequency of the wave depends on what the source is doing. If you put your feet in the pool and you kick your feet back and forth 3 times a second, then you are creating a wave of exactly that frequency. Now, the velocity of the wave we saw this definition in chapter 23, that the index of refraction is c divided by the velocity of the material. And so, the velocity in the material is really dependent on the stuff, right? What the wave is going through. And that's what the index is trying to tell us. It's trying to tell us that, different transparent materials will have different velocities that it allows the wave to go through, because there's this absorption of the wave and then this reemission of the wave. And so it slows down the waves from, going their normal speed in vacuum. And so it slows them down a little bit. So the velocity of the wave, this really depends on the material, or, maybe a better word here is the medium that the wave, is traveling through. So you change the material, the wave will travel at different speeds to that. So something like air, sound kind of goes through air about 700 miles per hour. And that's about 340 meters per second. But if you hit a hammer on the railroad track, that vibration, that wave will travel something more like 5,000 meters per second, more than 10 times the speed, because the material is different, right? The molecules in that solid piece of steel are closer together, so they hit each other more rapidly, and that vibration travels out much quicker than what happens really with something like sound waves. And then that leaves the last part here, and that is the wavelength. And so take a look here. The wavelength equals, the velocity or the frequency, and that velocity depends on the medium. And this frequency depends on the source that created the wave. And so the wavelength really is dependent upon both of those things, right? Because the velocity is dependent on one, the source is really creating the frequency of the wave. So the wavelength is dependent upon both the medium and the source. And so, that's something else we have to really kind of pay attention to. So, the wavelength is, really dependent on both the source and the medium. Okay, so that's a review from really last semester. And I think we maybe started off this discussion with some of these things again, but just kind of keep in mind, right? This wave equation right now is the mathematics, and it's the only mathematics that we really need that describes what's really kind of going on with the wave here. And so eventually we'll have to use some of these concepts here as we start going through the properties of waves, and then seeing exactly how that pertains or doesn't pertain to electromagnetic waves. Okay, so so far so good. So I think we've seen most of this kind of stuff before here, and so maybe this refreshes you a little bit on this, and so let's kind of take this a step further here. Okay, and what this means here for what we're going to discuss today here. So topic number one, Huygens principle. And if we were allowed to be doing demonstrations in front of you, if you were in the laboratory, what we would be using for our light sources would be just little lasers. In today's world, they're very cheap, right? They cost, $8 or $10 or something like that. But the laser beam is very intense. There's a lot of photons there, so it's very bright. And so if we hit a piece of glass or a piece of plastic, we can see the laser beam, especially if we turn the lights off in the room. We can see it. We can see it hit the material, and you can see it, scatter through that material. And so you can really see something that looks like a line, going through the material. So when you are looking, at using something like Snell's law, and you're drawing this beam, and then, it refracts at a certain angle and these types of things, that's exactly what you would see in the laboratory with a laser. Okay, now the pioneers of this material, this goes back about 200 years or so, didn't have laser beams, right? They're going to be created in the 1960s. And they're going to have a more difficult time than we're going to have because they could not get as an intense light source as we could. But they certainly were very clever people, and they were able to kind of carry through these experiments with precision. But it's worthwhile here to look at something like Huygens principle, and it's it's stated this way. And it's worthwhile to try to figure out exactly what this means. Every point on a wavefront is a source of tiny wavelets that spread out at the speed of the wave itself. Okay, the new wavefront is the envelope of all wavelets and is tangent to all of them. Okay, and so what Huygens is really allowing us to do is something we've already been doing, and none of you have really sort of challenged it at all. We've been treating light like a line, but it's not a line, it's a wave. Okay, and so if you have a light bulb here, and you turn this on, what happens is that you have these waves that move away from the light bulb. and they move in all directions. So it's really like a sphere, right? The light goes in all directions here. I'm only going to draw it in one direction. And here's kind of the deal, when it comes to waves. And so it's kind of worthwhile to understand, exactly what's going on here, right? If you look at a wave and you look at, a side view, what you see is something like that, right? You see some disturbance going through the material, so the material moves up, it moves down, and then the wave propagates at right angles to that up and down motion here. Now, if you turn on a light bulb, these waves really move away from this light bulb, and it's pretty common to probably start seeing some sort of picture like that. Okay. And this right here is the top of that wave. This right here is the top of that wave. This right here is the top of that wave. Okay, so these are just multiple waves, right? The light just kind of keeps giving off waves. So when you're looking down, right, this is a down view here of waves. What you see people end up doing is drawing the wave top, okay? And so the wave top then is just this little kind of like line that I've got up here. Okay, now let's take a look here at Huygens' principle. And Huygens' principle says every point on a wavefront. So here's a wavefront, and so there's a point, and here's a point, and there's a point. Okay, so I can pick any points. I can pick them all, right? Point by point. On a wavefront, so every point on a wavefront is a source of tiny wavelets that spread out at the speed of the wave itself. So in other words, you can imagine this point right here as being a source of tiny waves, like so. Okay, and you can imagine, this other point here as a source of tiny waves, as well, and so forth. Okay. The new wavefront is the envelope of all the wavelets and is tangent to all of them. And that's really the key here, okay? That the wavefront is the envelope of all wavelets and is tangent to all of them. And so, in other words, this wavefront can be thought of as a line going through that source of wavelets, that little point here, as long as it hits the wavefront at right angles. And then it goes through here at right angles, and then it goes through here at right angles. And so that ray right there is perpendicular or tangent, right? Tangent, perpendicular to the wavefront. And according to Huygens, we can approximate, right, this kind of motion with a line that goes right across the wave tops as long as it goes across them at right angles, okay? And so sometimes the physicists will refer to this as the ray approximation of the wave. Now, when you're in the lab, you just kind of get used to seeing laser beams just act like little light, little lines kind of going here and there and so forth, because you don't sort of see, the light spreading out. It stays very collimated, which is a property of laser light. So it's a kind of a special light that we normally don't see in our everyday life here. So we have this principle here that says, okay, what you really can do is kind of get a ray that goes across the top of the waves and it's tangent to them. And that ray then is in the direction of the propagation of the wave. And, for the most part, in today's world, it's easy for the students to believe this, but maybe historically not, because, more than 50 years ago, we didn't have laser beams that you can see behaving like lines, right? So you would just, have light sources, and, you can, certainly use filters and, get a light that is a certain color, and you can get it fairly bright, and, you can watch that little beam kind of, reflect off mirrors. You can certainly see it, transmit through transparent materials, but probably nowhere near with the clarity that, we really kind of see this today. Okay. And so this is to let us know that, okay, treating light like a line is a principle, and this is supposed to work. Okay, and so one thing that we should do is maybe kind of put this to the test, and if it works, and then that makes our life easy, because lines are very, very easy to behave, to understand their behavior, and to do the mathematics for them. So we kind of like straight lines, and this makes our geometry so much easier to deal with the straight lines, as opposed to dealing with this kind of serpentine motion of material, moving in one direction, and something like the wave and the energy propagating in another direction. So probably in your package of stuff, you probably have some sort of funny looking picture that looks like this. So I just try to do the best I can here on the computer. But what you're looking at here is a boundary between two materials. Okay, and so let's just say that this is air over here. And let's say that this is a piece of glass, okay? Some sort of transparent material. And we have a light bulb right here. Okay, so you can see my beautiful computer drawing right there. I have a light bulb, and you turn the light bulb on. And what happens is that these wave fronts start moving away from the light bulb. They really go in all directions. I'm just concerned with the light that is going to transmit into this material here. Okay, and so here is a wave front. That's the top of a wave. Here is the next wave front. Okay, and so these are, the crests, or the top of the waves. So the distance from one wave to the other wave is the wavelength. So we're looking down on the waves here, and these straight lines then are the tops of the waves. Okay. The wave equation says distance, or that wavelength, equals the rate. And I think I'm going to put a little I right here, because this is the incident material. The light is starting in air. That's the incident material I'm just trying to transmit into this piece of glass. Is the velocity in that material times the period of the wave. Okay, or I could put the frequency, either way. And so what Huygens' principle says is that we can approximate this with a ray that goes right across the wave fronts, and it has to hit them at right angles. So it's creating these right angles here. And so here's our Huygens. It's not how you spell it. It's not Huygens. So here's our Huygens ray right there. Okay. And this right here is the normal line. So here's the boundary. So this is the top of the piece of glass right here that we've got going. And the glass then is, the rest of, the piece of paper. So this is all glass, going this way. All right. And so I put in that dotted normal line. And so this right here is the incident angle. So really, waves are moving at the speed of whatever the wave is in that material. So in something like air, it's really very close to 3 × 10⁸ meters per second. And I'm going to cut across those wave fronts with this Huygens ray. and it has to be at right angles to the wavefronts. And, so I can see that this is my incident angle with the normal line, and in this material right here, this is the transmitted angle. Okay, and so those are the definitions that we see in Snell's law, that the incident angle is the angle that the light hits the material as measured from the normal line. And then the transmitted angle is, the angle that the light path is taking in the material as measured from the normal line. And so, I think, there's some geometry here that we can do, but straight lines are very, very nice to really kind of be dealing with here. And so, that's really, the important thing here. And so let's kind of create some geometry here. And I'm going to call this here maybe point A. Maybe I'll call that point B. Maybe we'll call this here point C. Okay. And if I were to start doing some geometry, I think you'll see, very quickly that the incident angle is also right here. That is, this angle right here that I just drew in is congruent to that one right there. And so, no big deal. But let me see here. This side right here is this long. In this triangle. So I'm going to look at that triangle right there. Okay. Now in that triangle right there, what I'm going to do is just some right triangle trigonometry. And so maybe I'll do that down here. Okay, now the sine of the incident angle is the opposite side, all divided by the hypotenuse. So the opposite side is the wavelength, all divided by the hypotenuse, which is just the length of E to C. And okay, I don't know what that is, but right now that's kind of enough here. Okay. And now what I'm going to do is look carefully inside of the material that the light is transmitting into. And I can get a ray that goes across, right? So here are the wave fronts right here, or the wave tops. And I can get a ray that cuts across those to approximate those, like so. And it has to cut across at a right angle here, right? So they got to be, hitting these wave fronts here at right angles, just like so. And I'm going to look at, this triangle. So let me put a letter, maybe D right there. And I'm going to be looking at this triangle right here. Okay. And so when I look at that triangle, I know I have a right angle right here. And, I think if you did some geometry, you can convince yourself pretty fast that this right here is the transmitted angle, that this angle here is the same as that one there. Okay, and if you don't believe it, just start looking at, adding up some triangles and looking at some supplements and some complementary angles here, and you're going to pick that up pretty fast. Now, in that triangle, if I were to take the sine of the transmitted angle, that's the opposite side. Let me see here. I'm trying to rethink my geometry here a little bit. And as I'm kind of rethinking it, I think that is, come here, eraser. Let's, let me think about that some more. That angle, this angle. Here, this is the transmitted angle right here. Okay, so it's that one right there. That's the one that's going to be the same as this one. So I can see a right angle there. I can see a right angle. Yep, that's the right one. Okay, so very good. So the sine of that angle is the opposite side this side right there. And that's really the wavelength in the material, right? So this is the wavelength in the transmitted material. So that's the velocity of the wave in that material times the period. And so this is the velocity in the transmitted material times the period, all over the hypotenuse in that green triangle, which is A over C. Okay, so I think now I'm looking at the geometry in the yellow triangle and the green triangle with trying to get the incident angle and the transmitted angle worked into this somehow, some way. And so what I'm going to do here is something like this. I'm going to say that AC is the velocity in the transmitted material times the period divided by theta t. And then I'm going to kind of come over here and I'm going to do the same thing. Let's say is AC equals the velocity in this material times time all over sine of the incident angle. Okay, so what I've got here is A to C is equal to some stuff in both triangles. So it must be the case that this is equal to that right there. Okay. Now, using the properties of that we see in the wave equation that we just saw maybe like 10 minutes ago, the frequency of the wave depends only on the source, and the frequency of the wave has the same information as the period, right? T and F really don't have any new information from each other. And so the frequency of the wave and or the period of the wave depends only on the source. So those T's have got to be the same number. It doesn't matter on which side of the boundary they are on. The frequency of the wave does not change. It can't. You need an energy source to change the frequency of the wave. And a piece of glass is not an energy source to a wave. Okay, it doesn't do any work on the wave. So that T right there is the same as that T, because T is source dependent, and the source, that is the light bulb, has not changed what it's doing. And so it must be exactly the same number. So I'm going to cancel that off. And then I'm going to remember that the index of refraction is the speed of light in the vacuum divided by the speed of light in the material. Okay. And so maybe I'll just actually write that out. So the velocity of the wave in the material is equal to C divided by N of the material. Okay. And so I'm going to use this right here to make a substitution up here. So I'm going to take that velocity out, and in its place, I'm going to put C all over the index of refraction in that material, the incident material, and there's still this sign here. And over here, I'm going to take out that velocity, and that's going to be equal to C divided by the index of the transmitted material, and then there's still this sign here. Okay, so speed of light in the vacuum is the speed of light in vacuum, and then I'm going to take the reciprocal of both sides. And you know what I'm left with here then is Ni times sine of theta I equals Nt sine of theta t. Okay. So I did promise you several weeks ago that when we looked at Snell's law to begin with, it was just an experimental result. It was just something that Snell could measure and you know, really kind of figure out by looking at light going through transparent materials. But if we start with Huygens' principle, the law of refraction, Snell's law, pops right out. So Snell's law really is not an experimental result. It's really just a property of really waves itself. And so we have this ray approximation going across wave tops It leads immediately to some law that we know very well, and works in transparent materials, which allows us to understand what's going on with lenses and shaping them a certain way and using certain materials and so forth. So we have a well-known result here coming from something really like Huygens principle here. And so that's very, very nice to see something like that really sort of take place. So now I've got some confidence in really treating these waves as a straight line. And so I'm going to kind of keep plowing forward and just kind of keep doing that, and until something tells me that it's not working anymore, or something like that. So, but this works all the time, and so this is sort of a nice way to be able to take a look at that. Let's take a look here at waves in a medium and see what's going on there. And so, just like, since we've got, Snell's law basically right in front of us, if we have this boundary here where you've got, maybe, one index there, some other index there, and, light comes in, and we're going to approximate it with this wave now. We're going to approximate the wave with this straight line. And then we get this transmitted angle here. That's essentially the picture we've been looking at for several weeks now. But the wave that is in material 1 is the velocity in that material times the period, right? And the wave size in the new medium, if you have unequal indexes, is going to have then a new velocity, which means that you're going to have a new wavelength, but you can't really have a new period, right? Because that period depends on what created the wave, and that's someplace else, right? And this new boundary is not some sort of energy source that's doing work on the wave at all. So those T's happen to be the same. And I think what I'm going to do here, I'm just going to form this ratio to see how does the wave in one material compare to the wavelength in another material. And in one material, in the new material, right, it looks something like that. And in the original material, it looked like this. But those T's are the same number, so those really kind of cancel out. And once again, just with exactly what I did before, N equals C divided by the velocity in the material. So the velocity in the material can be written as really C all over the index of that material. And this velocity here can be written as C divided by the index in that material. And so when you do your step of algebra here and so forth, right, we're going to see that those cancel out, but the ratio of the wavelengths from one material to the other material, let me see, we have a fraction on the bottom of a fraction, so that becomes that becomes this. And, if we let, N1 equal essentially air, what you're looking at then is the wave in the new material, what I'm calling wave 2, is really then, so I'll cross multiply here. I have this index, which is 1. I'll multiply by that over N2. And so, maybe I can see that the wave in the new material is the wave that was in the previous material divided by that index. So in other words, the wave will slow down if you're hitting a thicker or optically dense material that has a bigger index. And so the wave slows down. And so then the wave has to get shorter because it's going slower, right? And so in distance equals rate times time, essentially that has to be a constant from one material to the next material. But V is not constant because that depends on the index. So then the wavelengths have to change. And we said that the wavelength was dependent on partially the material, and we see that it is, right? And so if you are going into an index, say from air into a piece of glass that has an index of 1.5, what you're going to do is just get the wavelength in air divided by 1.5, the index of the new material. And that's how long the wave is going to be in that material. And so suddenly Huygens principle is, we can get a lot of uses out of something like that. And I'm going to be using that here for probably the rest of this lecture and the next couple of lectures too. I'm just going to keep treating light just like a straight line. And so then this works out pretty nicely. Okay, so go back and refresh your memory that the frequency is only dependent on the source of the wave. The velocity is dependent on the medium, and then the wavelength is dependent upon what the source did as well as the new medium. You change either one of those, and typically we don't change the source. That means you're doing work on the wave. But if you change the material, then the wavelength changes, and we see exactly how that happens here. And so this is very, very nice. Okay, and so Huygens' principle really just simplifies our life. And so it's a good thing, right? It's stated in some funny language, but when you translate those words, you just cut across wave tops really with rays that hit at right angles. It makes your life much, much easier mathematically because, geometry is typically not terrible to deal with. So, okay, so let's take a look then at, one of these major properties that waves have, and that's this property of interference. And we did some stuff last semester where maybe I put down like a pulse on a hose. You get a garden hose and you kind of wiggle your hand up and down, and this pulse kind of moves this way. And somebody gets to the other end of the material and puts a pulse down that way. And as they travel and they're in the same space at the same time, they interfere. And then they pass through each other and they keep going. But we're in the same space at the same time. If they are both waves that were up high, they come and they create a bigger wave. But if this wave was up high and this wave was down low and they're in that same space, then they destructively interfere with each other. And so then they kind of subtract out. And it's possible that the two waves can go right through each other, create a spot with no amplitude, and then they keep going on their respective ways and so forth. So we looked at that a little bit here. And we're going to look at that much more carefully. Now, what we don't see happen is when you turn on a light bulb here and you turn on a light bulb here, there are waves then that are in the same space at the same time, and we don't see any kind of interference effects. And that's because the light waves are bouncing up and down so fast, and then the white light has reds, it has blues, and has greens, it has all these different wavelengths there. And to get waves to interfere constructively or destructively, and to maintain that so our eye can see it, you have to meet very, very specific conditions. And I can get interference of waves, say on a slinky, if I start wiggling the slinky up and down, and I can get something called standing waves on there, and that's really an interference pattern. So that can be done. And if you look at what really happens there, you have to make light waves match up with exactly those same requirements, which is not easy to do. And we just don't see it in our everyday life. Right? So just like when you have two stereo speakers and they're both putting out waves and you're out in front of them and you're hearing from one speaker and from the other speaker, you don't really notice dead spots or anything like that typically in the rooms. You're not noticing that the waves are canceling each other out because they're really bouncing off of the floor, the ceiling, the walls, and there's different wavelengths that are changing because the frequencies are changing. Unless you're listening to Yanni music, then it's just, than it doesn't. Otherwise, it's very difficult to have a wave just kind of sit still in front of you so you can take a look and see if this interference is really taking place here. So it's something that you have to kind of try to slow down a little bit here. And so when you're thinking through this, this is exactly what happened a little bit more than 200 years ago. And so Thomas Young is going to kind of look at this idea here. And this is going to be a very ingenious way of really kind of taking a look at what's happening here. Okay, so if you recall what we looked at last semester, it would be something, a little bit cheesy, but it would look like this. You would have a speaker, and you would have a speaker. And this speaker would be connected to this box, and this would be connected to this box. And this box creates a tone, okay? And so the tone could just be any frequency. So it just goes ma, and it creates this tone. And so usually it's, called an oscillator or something like that. So people put a little sine wave on there, but it's just a function generator. And usually you just kind of create a little sound wave there. And as long as both speakers are connected to the same box, they're creating exactly the same frequency, right? So the frequencies aren't changing. So it's not music where you're playing different notes or anything like that. It's just making one complete tone, okay? But there's something else that's important that's happening, is that when the waves are going down the wire, right, there is electrical impulses. And then through actually something like electromagnetic induction, we get the cone of the speaker moving at exactly the same rate. So it starts pushing the air at exactly that same rate. And it starts creating this wave that comes out of the speaker that is essentially identical to what's coming out of the other speaker. And that's important, right? So, so if you had a spot out here, and let's say the wave that comes out of here, looks like that. And then if these were exactly the same distance, what we would have at this location right here is that these waves are, we use the words, in phase. And what that means is that the waves are exactly in the same part of their cycle, right? So the cycle of the wave, right there, that's one wave. It's got to go up, it's got to get back to where it started, then it's got to go down and get back to where it started. So this is one wavelength. And at this spot in space, this spot right here that I'm talking about, it doesn't really matter where the wave is in that cycle, as long as both waves are in the same place of that cycle, then we say they're in phase. And that's a good thing if you want the waves to add up, to be constructive interference, okay? Now, if I pick another spot, right? So, maybe I picked a spot over here. Let me get a totally different color. Let me see, so maybe just about like right here, okay? Or the wave coming out of here was able to complete itself, but see, the wave coming from the top speaker has farther to go. And so maybe it completes itself right there, but now it only has room to complete half of itself. And so the wave coming from the top speaker now at that spot is really diving down. The wave coming from the bottom speaker is diving up. They're completely different places in their cycle. And we say that they are out of phase. They are doing something different, okay? If they are in phase, then we say that that is constructive interference. If they're out of phase, this was destructive interference. If they're in phase, we call that constructive interference. Okay. So what Thomas Young is trying to do is see, does light behave like, you know, what's happening here with the sound waves? And so what you need to do here is repeat the experiment, but not with sound waves, but with light waves. And so what you need is two sources of waves, just like two speakers, but the wave that's coming from both speakers or from both sources of light have to be doing exactly the same thing. With sound, it's pretty easy. You just get two speakers and you hook them up to the same sound generator. And so as long as the same sound generator is feeding both speakers, what comes out of both speakers is identical. Okay. And the waves are starting in exactly the same place when they come out of the speaker. And so Thomas Young has to match up those conditions perfectly. Okay, and so this is something that, you know, is kind of important for us to understand really what's taking place here. But maybe we'll put this down like this, you know, to maintain is key. This is what we don't see in our everyday life. We don't see light waves interfering in a way that the interference is being maintained for a long time. There's light waves in the room right now that I'm in. There's light rays that are in the room right now that you're in, and they're interfering constructively and destructively, but it's happening so fast that we just sort of see this average overall effect, and we see really no changes at all because the interference is not sitting there being maintained in a certain location in space. So to maintain really interference, the waves, right, two of them must be, and there's really two conditions here. One is that they must be monochromatic. And that really means one wavelength, or it means one frequency. Okay, so if the waves are changing their length somehow, all right, so in other words, if I come up here and I put my head right here in this spot, okay, so here, okay, so here's you. There's an eyeball, there's an eyeball in your physics class, so of course you got a big old honking smile on, and so you put your ear right in that one spot. For that to be an in-phase spot and to be maintained as an in-phase spot, you have to be using a wave that is exactly not changing its length, right? So if you go over to the dial on the oscillator, you start changing the frequency, then the waves start changing, then what happens is that your ear is something completely different, right? Because you picked magically, geometrically, the spot where both waves are traveling exactly the same distance. And so they have to be in phase. And now if you start changing the wavelength, that may not be the case, right? Yeah, especially if you're in a different spot. Here, this is kind of the magic spot that they're kind of always going to do something like that, probably. But for your ear to be hearing, you know, something in phase, which would be loud to your ear, you need to be not changing the wavelength. And you also need both waves. The waves must be coherent. And coherent is a word that means that their phase or their phase difference must be maintained. Okay. With sound waves, this is pretty easy to do. With the typical way that we create light waves, it's not easy to do. And so a light bulb, an incandescent bulb, has a wire going through it, and it has resistance. So you put a current through it, and that resistor gets warm, and it starts giving off these waves then. And those waves are created by the electrons that are getting pushed around because you're trying to push current and you're slowing this current down. And so the light that comes off of a light bulb is constantly changing what it's doing, because the wire is not always doing exactly the same thing in terms of how the waves are coming off of that here. And so coherent, what it really means, is something like this. If you have a source of waves here, say it's a speaker, and the wave starts here, maybe right at the beginning of the wave, and it's doing that, that's okay. And maybe here, the wave is starting here, and it does that, right? So these two waves are starting out of phase from each other. But as long as you maintain that out of phaseness exactly the same, you're okay. Okay. And that's what it means that it's coherent. Now, if I start changing the wave at one speaker on how it starts coming out of the wave, where it starts in its cycle, then you're not maintaining coherence. Then you have an incoherent source, and the light rays that come out of light bulbs, that come out of flashlights, that come out of your headlights in your car are totally incoherent, right? They're just a complete jumble of waves, and they're certainly not monochromatic. So we just don't see this happening, in our everyday life. But these are the conditions that Thomas Young has to kind of match up with if he wants to show that light might have this property called interference. This was not a very popular thought 200 years ago, because the giant of the day, Newton, he preceding this by 100 years or so, weighed in and said, light is a corpuscle, essentially a particle, and if waves can be shown to interfere, then they're showing wave properties, and then it seems like they're not acting like a particle. But most people were probably, if you're a betting man, you'd be betting whatever Newton said was probably right. And so Young is going to say, well, okay, sound waves might be able to do this, and so let's see if we can do this with light waves. And so he did this in a very, very ingenious way. Okay, he gets a light source. Okay, and so I don't know if it's a light bulb, it could just be a candle or something like that. Okay, so it could just be a candle. All right, so you got a candle, and light waves are coming off of it, and then he puts probably like stained glass in front of it, something that's going to filter out the light that's coming off of the candle, because it's all kinds of wavelengths. And so he puts a filter up here. Okay. So maybe it's a yellow piece of stained glass. So the light that comes through that then kind of has this yellowish color, or it could be a piece of green, or whatever color it happens to be. And so that filter is essentially giving him that condition right there, getting one wavelength of light to be in this space here. Okay. And then he needs the waves to be coherent. So the key here is waves. He needs two sources, just like two speakers, and they have to be coherent. And so what he does, is get some sort of material. In today's world, what you can get is something maybe like aluminum foil, and you can get maybe like an X-Acto knife, and you can just put little cuts into it, okay? Little tiny cuts. And those are the slits. Okay, and so you've got two slits there. And so when the waves hit those two openings, essentially each opening is acting like a speaker. Each one now is a source of waves, okay? And they're monochromatic waves, and they're coming from the same source. So now they are going to be coherent with each other, okay? And so the waves that come through here will bend at this opening. That's called diffraction. And then the waves that are coming from this other opening bend, and they do the same thing, okay? And so here we've got two wave fronts in that spot right there, two wave tops that are in the same space at the same time, right? So this right here would be a point of constructive interference. This spot right here, you see I'm in between that wave and that wave. So those are the two wave fronts, and I'm right in the middle of those, or pretty close to that. So I'm at the bottom of the wave. But for this wave, I'm at the top of it. So one wave is at the top, one wave is at the bottom. This spot right here then is a spot of destructive interference. So this spot of constructive interference is two waves, and they're up high, and they're hitting each other, right? So you've got a wave like this, and you've got a wave like this, and they're hitting each other in the same space at the same time. And so they're in the same space at the same time, right? The two amplitudes add together, and you get this big wave here, right? You get constructive interference. Destructive interference, you can think about that as, one wave is kind of like down here and it's traveling that way, and the other wave is kind of up here and it's traveling that way. And when they're in the same space at the same time, they can subtract out. If they start off with the same amplitude, you get no wave right there, right? One wave is down here, one wave is up here, like here. When they're overlapping, there's no wave right there very briefly, then they pass through each other. But there's a spot right there that has a destructive interference place, or a little region of destructive interference. But the clever thing here that, and it's not that hard to do, is if you put, say a wall or a screen like right here, this spot maintains destructive interference. Okay? This spot right here where the two wavefronts are hitting is a spot being maintained of constructive interference, and it's maintained. It just sits there, right? It just sits there. And so this is something we don't see in our everyday life, but that's exactly what Thomas Young is able to show, and this really happens, okay? And so you'll have some very nice, pictures in your textbook that are really sort of well worth looking at here. And so, you might have these, if you have a yellow filter here, you've got these yellow wavefronts coming in, hit those openings, they bend a little bit, and then you have two sources of waves that are coherent because they're from the same source. They're monochromatic because they went through a filter, and now they're in the same space at the same time, and the interference is maintained. That means it just sort of sits there. It doesn't go anywhere, okay? And so if you are looking, here we're looking down on the experiment, right? So we have a little candle, we're looking down on it, and we can see, the tops of the waves here, right? So we're looking down here. And we're looking down on these two little openings, the two little slits, and then, the waves go through here. And I'm looking down on, what I put here as the screen. Now, if I were to change my point of view and I look straight at the screen could just be the wall, right? So you just have two little openings, let the light go through, and then eventually the waves hit the wall. But on the wall, what you see is what we call an interference pattern. So let's call this here number 2. So on the screen, an interference pattern is observed. Okay, and so let's say that you know, the two openings, the two little slits, are kind of right in front of us. The waves have gone through them, and when you're looking at the screen, so maybe here's the screen here. What you get is a spot where the two waves add together, and it's light. And so you see a bright spot on the wall, okay? And that's a spot of, now we're looking straight onto the wall. So this is a spot of constructive interference. And then there's another spot of constructive interference and another spot of constructive interference. And then over here, you have a spot of constructive interference. And here you got a spot of constructive interference. Okay. But you also have spots of where there is no light on the wall. I mean, literally no light. It's just, you know, so you darken the room, you put the light through the two slits, and the light that hits the wall kind of is like polka dots. You just have spots here and there, and these are all regions here of destructive interference. And the physics here is not very complicated. It's not very hard, but a lot of times how people talk about this is really the problem here. But this is the interference pattern that you see emerge, you know, on the wall when the light goes through, monochromatic light from the same source goes through two slits. You see regions that are very bright, and then spots where there's no light, and then bright, and then dark, and then bright, and then dark. And this pattern is given really some labels here. And so if I blow up that picture, and maybe it looks like this, and I'll you know, if you're really kind of paying attention, you'll see how this makes sense here. This right here is called the central maximum. Okay. And that really is the spot right in the middle of the two slits. Okay. So if you have a series of two slits, if you go right between them, and then here's the wall, this right here is a bright spot. And why is that a bright spot? Well, you can almost guarantee that this wave and that wave, since it's right in the middle, have traveled exactly the same distance. So they've got to be doing exactly the same thing at the same time. Okay. And so we call that the central maximum. And then we count off bright spots from there. And the pattern is symmetric. What happens on the right side happens on the left side. And this is called m equals 0. That's how we name that spot. But there's a mathematical reason why we do that. And so I'll show you that here in a moment. Okay. Now, this over here is called m equals 1, and this is called m equals 1. Those are the first bright spots, or the bright fringes from the central maximum. Okay. And so this right here is m equals 2, and this over here is m equals 2. And I'll show you why we get those numbers here. But right now, right, it kind of makes sense. It's just labeling, right? So if you're the first bright spot on either side of the central maximum, you get this label of 1. If you're the second bright spot from the central maximum, on either side, you get a label of 2. Okay. So I think that makes sense. But this right here is where you have to be careful. that this dark region right here, right? So there's this dark region right here where there is no light. That is a spot of destructive interference. And that is, now be careful here, right? You need to be careful because the first bright spot is called m equals 1, right? On the right-hand side. The first bright spot on the left side is called m equals 1. This right here is called m equals 0 for the dark spots. This is m equals 0 for the dark spots. This is m equals 1 for the dark spots. This is m equals 1 for the dark spots. So this is really, the second dark or destructive region. It's the second dark region off to the side of the central maximum, but it gets m equals 1. So we start counting from 0 on both sides here. Okay. And so if you start at the central maximum, you're just looking at bright spots, it makes sense. The first bright spot is m equals 1. Second bright spots are m equals 2. The first dark spots on both sides of the central maximum is where you start counting dark spots. That's m equals 0. So really, the first dark region is labeled 0, and then each dark spot after that gets a number bigger than that. And so we have to kind of be careful because here you have the number 1, and here it's really the second dark region here. So just kind of keep that in mind. Okay, so what is taking place here? Well, it's a mess if you think about waves by this pattern that I've got drawn up here. That is, we're looking down on waves and you've got, all these ripples kind of going, across the water or whatever, however you're thinking about these waves here. If you're thinking about them that way, you can see how messy the picture gets very, very quickly. I'm going to think about waves using Huygens principle. Okay. And so let's actually take a look here at, the double slit experiment. Yeah, that's all it. And if this makes sense to you, there's really nothing very deep here. If this makes sense to you, then you really kind of get the whole thing. It's just hard for me to always kind of draw this some fashion. So here's our two slits. Okay. And waves are coming from the same source and they're going through, both openings there. And if I get this spot, right in the middle of the two openings, right here, this is where I get my central maximum, right here. Okay. And let's say that the wave that comes here, I'm going to approximate it as a ray that hits that spot. And here. Okay, now from the bottom wave, I'm going to call this path 2. And so I'll call that delta 2. And I'll call this up here path 1, delta 1. And let's say that the wave is precisely the length of those two rays that I've got. Okay, and so, the wave looks like this. And it completes itself right there. And down here, right there. So the two waves are completely in sync at that spot, right? And so they are in phase. If they're in phase, then they add together, their amplitudes add together. And so then you get a bigger wave, right? It's just like one crest and another crest, they come together and they add up to something that was bigger than both of them, right? So now they're adding together. But take a look here. I get a bright spot because each wave is in sync. And so what's really important is really the path difference. That's going to be really important here. And so the path difference of the two waves, and it doesn't matter which one's, going first here, so I'll put it in absolute values. So that's the path difference. How much longer has one wave traveled than the other? And in this spot right here, it's 0, right? They have not traveled any path length difference. They've both gone exactly the same distance because we're right in the middle of those two openings here. Now, if I go over to the sides, and here I'm looking down on the screen, if I go over to the sides, then that's not the case anymore, okay? And so let's say that I get my next, bright spot here. Okay. Just kind of watch what happens here. You probably can't do this on your paper, but I think we can do this here. So I can get rid of all this here. Okay. And I've got the wave coming from this opening, hitting here. And I've got the wave here, hitting there. Now notice that path 2 is longer now, right? And so if path 2 is longer, and I'm getting a bright spot here, that means the two waves have been able to land in sync at that spot. And I don't have this drawn to any sort of great scale here. Let me see here if I can. Yeah, I'll just make this work here. If I were to drop something down right here, a straight line, and create a right angle here, then this piece right here and that piece right there are the same length, essentially, right? So I've got these two pieces that are the same length. So this little piece right here is the path difference. It's how much longer ray number 2 is than ray number 1. That's the path difference. Okay, and so the path difference is just, how much longer is one of those paths than the other path. And now if this is a bright spot up here, what that means is that an entire wave, so let me get a different color here so it kind of shows up. An entire wave is sitting right here. So there's one wave, okay? 2 waves, 3 waves, 4 waves, 5, 6, 7, 8, 9, or something like that, okay? And then, since this and that are the same length, this is going to have exactly how many waves I've got here, which is 1, 2, 3, 4. So I think that was like 8 waves. So 1 wave, 2, 3, 4, 5, 6, 7, 8. So they land here in sync. But for this to be a bright spot over here, the path difference is off by a whole wave, so that a whole wave can fit into that spot right there. So that's why I was mentioning that I probably don't have this drawn up to scale here, perfectly. What you would have to do to get this really, really nicely done is probably put, but that's the idea. So if I could try to get this to scale somehow for you. I'm going to stretch out the waves. They're not going to look great to your eye, but I think it gets the point across here. Here's the two paths. And, let's say that, here we had one wave, but now if this is a bright spot, here's the wave, and then here's the wave again. And so notice that one path is holding one whole wave more than the other one, okay? So in this spot right here, both paths have exactly the same amount of waves. The next bright spot is holding one more wave, right? This has one more. The key is whole wave. If it has one more whole wave, then the path difference, the difference of those two paths is one whole wave, right? One wavelength. And that's what the picture shows. If you go to the next bright spot up, then the path that is longer, it'll have two whole waves that are fitting in to that extra path difference. And see that, right? That one right there, that's M. So M equals one. One whole wave difference. Here, when I say here, that spot, there is no difference, zero difference in path. And so I have zero wavelengths difference into that spot. If I come down here, this is going to be a spot that has a path difference of one whole wave. And so that's why we call that M equals 1 right here. So when you look at the pattern, looking straight at the wall, this M equals 1, what that means is that the path that is longer to get to that spot is holding one wave more than the other one. When you hit the next bright spot, that's even further down the screen. So I've got more room. I can come down here from the central maximum. When I hit this spot down here, I'm going to see that, I'll change color so it kind of shows up that, right, here's one path to hit this spot. Here's the other path to hit this spot. This one that's longer holds two whole waves. It's got to be whole waves for them to be in sync, to be in phase. This spot right here, the path difference, so the difference is just one number minus the other, is holding two whole waves, and that's what that M is. So that M is just really a counting number of how many whole waves happen to be landing in the spot here, okay? And so that's why we get this labeling. Okay, so the mathematics. Okay, let's go to the mathematics here. So if that idea is making sense to you, then you've got the whole thing really kind of figured out here. And so even though I don't have this drawn to scale really, well at all, say if this holds like one wave, and this one has to hold two whole waves more. So 1, 2, and then 3. But the waves really need to be exactly the same size here. And I just can't, get the geometry here in front of me because they'd be so small you wouldn't be able to see them. But that's the idea here, right? That they are here in phase. Okay. So if that idea makes sense to you, you really kind of have this whole thing figured out. So this is how we get the labeling. And now let's take a look at the mathematics here. Okay. And so instead of just going to a new picture, I think what I'll do is just kind of get rid of some of this stuff here and clean this up. And I'm going to just go to this spot up here. Okay. And I'm going to drop this back down here. And this right here is the path difference. That's how much longer the bottom ray here is than the top ray. And the path difference, so I'll call that 2, I'll call that one 1. in this case, is a whole number of waves or something like that, right? It's got to be a whole number of waves for constructive interference. So, once again, if that makes sense to you, you really kind of have it figured out. But now what we need to do is get the mathematics involved here. And so this condition, a whole number of waves, this is for constructive interference only. Yeah, I'll take a look at what happens when we have destructive interference as well. What you control here as the experimenter is the color of light, because it's your filter, and you made the two slits, and the two slits have got a certain distance between them, and so typically that's called D. And there's this little triangle here that's getting formed right there. And, if you were to look at that little triangle, that you've got, there's D, we've got a right angle here, and there's this angle up here. And this is really the path difference right here, right? So this side right here is the path difference, how much longer one ray is than the other. And that's got to hold one whole wave or two whole waves or three whole waves for us to get constructive interference. And so, if I were to look at that little triangle and what I control as the experimenter is D, I would know what that number is. And it looks like the sine of that angle is the opposite side, the path difference, all over D. So in other words, D times the sine of theta equals the path difference. And I'm going to substitute that right there. Okay. And so this is really for constructive interference only. What needs to be true is that my path difference to hit these bright spots has to be a whole number of waves, but that's equal to D times the sine of that angle there. Okay, and I control how far apart I build these slits, and they're really close. They're like a fraction of a millimeter, like a quarter of a millimeter typically. These types of things. So they need to be, just very, very small cuts. So they're kind of almost hard to see with your eye. What you don't have here is any good way of measuring that angle. That angle is really very, very difficult to measure. And that's this angle here in this triangle that's up here, right? That's this angle here. So it's right there. Now, if you're clever and you start looking at the geometry of the situation, I'm going to go here. I think you can do this on your own. Let me see. This is okay. This is right in the middle here. So now let me get to something that really stands out. That's right in the middle. That's right up to that spot right there. This angle right here, from the central maximum to the spot that we're looking at, this angle is that angle right there. Okay, and so the two triangles are different sizes, but I think you'd be able to convince yourself pretty quickly that they've got to be the same. There's a right angle there, there's a right angle there, and so forth. And this distance between this bright spot and that bright spot, people call that Y. On the geometry, from where your slits are to the wall, people call that L. Okay. And this angle is a problem. But if you see these slits, they are just like hair. It's like a hair between them. Okay, and they're very, very small. And your screen is meters away. And so this distance compared to meters is very, very small. And so this is a way to get rid of this angle that is really a problem here, okay? And so you can try this. And so this is an approximation, okay? So it's called the small angle approximation. And some of you have seen this in a calculus class. That the sine of an angle is just about equal to the tangent of the angle. And you know, this kind of makes sense here. So if you have a small angle, a little tiny angle, like we do, this is a right angle, and here is the angle right inside of here. Okay, the sine of that angle is y all over the hypotenuse, right? So the sine of that angle is y all over the hypotenuse. The tangent of that angle is the opposite all over the adjacent, which I'll call L, okay? But you can see that H and L are almost the same length. And so you can try this on your calculator, get something like 2 degrees, take the sine of it, get 2 degrees, take the tangent of it, and you'll get something that is very, very similar if you're in the radian mode, right? So these are 2 lengths here. So, you know, we need to be in the radian mode here. And so the tangent here is just about the same as the sine, okay? And so we kind of come over and say, well, okay, this is just about the same as the tangent. And the tangent is the same as y all over L. And that is then the working mathematics for constructive interference. Because we control that because we make the slits. This y is the distance from one bright spot to the next bright spot. That's measured. And so when it's sitting there on the wall in front of you, you just put a ruler up and they're a few inches apart. L is the distance from the screen to the slit. And then M is just what bright spot we're looking at. Is it the first bright spot from the center or the second bright spot from the center? And so we just put in that number. Thomas Young, 200 years ago, 220 years ago now, has now a way of being able to, with a ruler, essentially, measure the wavelengths of light that we see. And this is what I usually would have you go to the laboratory and do. I'd give you I would do this probably in front of you. I would use a green laser. And then I would just bring in some double slits, let the laser go through to the double slits. We'd see the pattern on the wall, and I would just run a ruler to the wall. That would be L. I would get a ruler, and I would just measure Y. I would look on the little slit because it's made by somebody, and it's really just like a piece of aluminum foil, and they just make a couple little cuts in it. But their machine, you know, cuts it at precise distances, so we know what D is. And I would solve for the wavelength of the green laser. And we know that the light that we see, we human beings see, is between 400 and 700 nanometers, and green is right in the middle. And so my green laser actually has a stamp on it made by the manufacturer of what wavelength it is. And usually, you know, just using a ruler, I'm off by 1 or 2 or 3, 4%, something like that, very small. And then I'd have you go to the laboratory and give you a laser of a different color, so you wouldn't know the answer. And you measure the wavelength of light here, okay? And so this is, you know, what you end up doing here. And so what we've got here then is the condition for constructive interference. The 2 waves have to be traveling and landing in that spot in sync. So one wave is traveled a longer distance, and it has to then be a whole number of waves. Or M could be 0, or they're landing in the middle, and the 2 paths are exactly the same length. Or it's 1, or it's 2, or it's 3, and it actually goes on forever, but you just can't really see them. They become less and less intense. And what we do is we approximate out the sign for a y all over an L. Okay, where y is the distance between the bright spots, sometimes called the bright fringes. L is the distance from the slits to the wall. So if you're looking down on this experiment, if you're looking down and you have these two little slits, and of course I'm exaggerating just how big they happen to be. This right here is L. And so if you're using red laser light, you get a big red spot right there. And then you get this spot up here. Okay, so here's m equals 0. This might be then the first one up here. This right here is y. That right there is L. And this is the trouble angle that we really don't have a good way of measuring. So we approximate that angle away with calling the sine the tangent. And so sometimes that really bothers you that we're doing an approximation here. And I'll show you a little bit in a while of maybe why that's not really much of an issue. Okay, now, so there's really nothing here that's very deep. The one path from the top slit to hit m equals 1 is shorter than the bottom path. So the bottom path is longer, and so it has to hold a one whole number of waves, and the next bright spot would be 2 whole waves off, and so forth. And so if you have a dark spot here, right? So we have this dark region right here. What that means is that the wave that is traveling from one slit to hit that spot. So we've got our bright spots like this. The one that hits this spot and the one that hits that spot, they're off here. And so this might say like hold a whole wave, and here's like a whole wave, but then it only completes half of itself right here. So you're off now. Now they're out of sync, right? So now you've got destructive interference. And for this spot right here, for the destructive interference, the path difference, right? One of those rays is longer than the other. So the path difference is like a half of a wave. And so we want to count them exactly the same way. And so usually what ends up happening is something like that. So this right here is m equals 0. And so when I put in m equals 0 here plus 1/2, this tells me, oops, I'm sorry. This tells me that the path difference is a half of a wave. And so this is why we start counting this way, so that the destructive interference is counted the same way as the constructive interference. This right here then is exactly the same thing. This is d sine of theta, and we approximate that away like so. That's a 1/2. So here is the mathematical condition for destructive interference or dark fringes, the regions of darkness. The regions, the dark fringes, are off by a half of a wave, or 1.5 waves, or 2.5 waves, or something like that. And so, the idea is just that if you have spots where the 2 waves are completely in sync, then one of them has traveled a whole number of waves more than the other one. If you have regions that are completely dark, then you've got one wave is only completing half of its cycle, or the other wave has completed its full cycle. And then you've got, you're off by a half of a wave. And then that's going to give you a destructive interference spot. And so it really just comes down to understanding that picture right there, right? That it's this right here. That is the path difference. That path difference from the longer wave to the shorter wave, if it holds a half of a wave, then it puts them completely out of sync at that location on the screen. And then so they're going to be one wave diving down, one wave diving up. They destroy each other. You've got a dark fringe right there. Okay. And so for the first dark fringe, you put in m equals 0, and that gives you then the wavelength times a half, or a wave over 2. A half of a wave gives you the first dark fringe, because that's exactly what happens in the picture right there in front of me, is that the top wave has gone a half of a wave more than the bottom wave. The next dark fringe, the paths are even more skewed, and so then the longer one has gone 1.5 waves more. But as long as you're off by that half, that's what really matters here. Okay, so there's a little bit of this approximation in here, and like I think I mentioned that sometimes this is bothersome to students, but it really shouldn't. So I'll show you some data here in a little bit of why that is it. Eventually, the scientists have created a method for measuring that angle with precision. And, and we've got several of those devices in the college, and a lot of times I would have you go in and use those. And that way there is no approximation, but this is a good way of doing it. Probably not the way that the professionals would be measuring wavelengths of light today, since we have devices that can measure an angle, to probably, the nearest hundredth or thousandth of a degree. And so if you can get to that precision on an angle, then you don't worry about that approximation. And then you've got, these very nice devices that look like little funny telescopes that got little arms that move around and things. And so maybe we'll take a look at those here in a few weeks. Okay, so this guy right here is something that we just need to know. And this guy right here, we need to know. Those are the working results with some approximation for the conditions for constructive interference and for destructive interference. And for the most part, unless you've got one of these devices that, I'm referring to, this is the way that you're going to probably measure wavelengths of light that, exist in nature. And so let's take a look in and see how that kind of works out here. So let's scroll here a little bit. Okay, so let's take a look at this example here. It says a viewing screen is separated from a double slit source by 1.2 meters. Okay, typically I'd have you use a very, very big distance. But the professionals would have something called an optic bench. And most universities would have one of these. And it's a big table, and it's made out of steel usually. So it doesn't move, and it's very stable. And it's precision drilled at about, like a grid. So it looks like almost like a graph paper. And you can, kind of screw things in those different drill holes and know these distances, with precision. So, they're very expensive here. So you can do this on a small scale and not worry about, your percent errors or anything like that at all. So, what's happening here is that we've got, okay, 2 slits, and then over to the wall. This right here is 1.20 meters, okay? It says the distance between two slits is 0.030 millimeters. Okay. So that's this distance right here. The distance between the slits. So that's D. And D is, like I said, a fraction typically of a millimeter. Okay. The second order bright fringe is 4.50 centimeters from the center of the pattern. Okay, so here's the center of the pattern. So you get this pattern that looks like this: bright spots, dark spots, bright spots, dark spots. And this right here is m equals 0 for that spot. This is m equals 1 for that spot. This is m equals 2 for that spot. And this is m equals 1 for that spot. This is m equals 2 for that spot. Okay, so you just kind of see that there's a sort of symmetric pattern taking place here. And it sounds like to me that the second order bright fringe, the second order is this one right here. It's the second one. Second order is 4.50 centimeters from the center of the pattern. Okay, so that's this distance right here. So you would just measure this. So from right here to right there is 4.50 centimeters. Okay, and they want us to determine the wavelength of light being used. Okay, and so since these are bright fringes, that means this is constructive interference, right? So this is a place where the waves have traveled different distances, but they're in sync. And so the one that has traveled further has traveled a whole number of waves, 2 whole waves more. Okay. And so we need to put everything here in the same units, and it's pretty typical to be, just put everything in meters, I think. So 0.030 millimeters. I have to put that into meters. I just times by 10 to the minus 3. Y happens to be 4.5 centimeters, and so I have to move the decimal 2 places there, I think. And L is 1.20 meters. And I'm going to the second bright spot, and that's one equation, one unknown. And so the wave has to have a precise length here such that the geometry here holds. This is just all straight line geometry, and that really is it, right? M is just a counting number. But when you take a look here at your units, right, this meters cancels that meters, but it leaves this right here. So your wavelength will come out in meters. And so now it's just really a time to kind of go to the calculator. And, sometimes the professionals do this with light that we can't see. But, if it was something like in our classroom, we'd be using lasers that, we could see. And so let me try that again here, just to make sure that I get the same thing twice. That times that equals that, divided by 1.2. And then divide both sides by 2. And I think I get this here. So I've got the same thing a couple times in my calculator. Now 1, 2, 3, 4, 5, 6, 7. 5.625, 2, 3, 4, 5, 6, 7 times 10 to the minus 7 meters is the wavelength being used here. Okay. And so if I move the decimal here 2 places to make this bigger, and I think I'll just take it to that, I've got to make this 2 places smaller. And so this is 563 nanometers. Okay, so this is an experimenter that is using light that you and I can see, because we can see from 400 to 700 nanometers. So they're doing this visually. They're not using instrumentation, to find, the light waves and so forth. So you could do this with radio waves or something like that if you wanted to. But then your slits could be bigger. They could be like doorways, and you can do this experiment, on grand scales if you'd like to. So yeah, they're using 563 nanometer light, and so that's pretty close to the center of the spectrum that we can see from 400 to 700. So this is probably pretty greenish light here. So they're using probably a green laser here. I think my green laser is very close to 555 nanometers, so not much different from here at all. Okay, so using this condition that we have here is pretty easy, right? The math is not bad, but it's just a matter of kind of understanding this naming or this labeling of these spots here, and kind of picking off what's going on here. So a bright fringe implies constructive interference here. Okay. So let's take a look see here at this approximation. Okay, in a Young's double slit experiment performed at Stony Brook University, a distance of 0.500 millimeter electroform set of slits was used. Okay, their light source was the alpha line hydrogen, a very famous number, 656.3 nanometers. So in their experiment, L was 40 centimeters. Okay, the ninth order dark band was experimentally measured to be located so many millimeters on both sides of the center of the central maximum. What percent error has been introduced by the approximation that tangent is the same as the sine equals the same as the angle for small angles? Okay. So Stony Brook, a place that has huge physics labs, national laboratories, right? The people there are very, very serious about what's going on there and so forth. So they're using hydrogen, and this 656 nanometers is a well-known number. And this is usually something that I would have you go to the laboratory. I would give you a hydrogen source, and we would measure that number with no approximation at all. And then you're using a spectrometer to do that. And the spectrometer, what you're really paying for is a little bit of optics. There's a little bit of lenses and stuff in there, but you're really paying for is a very, very precise protractor. So the protractor can measure the angles on a spectrometer very, very accurately. And we would get this number here, 656. So what we're going to do is see what kind of wavelength of light comes out of the Young's double slit experiment, and we kind of know what the answer is here, right? So they're kind of telling us that this is the wavelength of light. Okay, so it looks like to me that they are looking at dark bands, that is destructive interference. And the condition for destructive interference is something like d y all over L equals m plus 1/2. We have to be off by some sort of multiple of a half wavelengths times the wavelength of light. Okay, and once again, I'm going to put everything in exactly the same units. Probably I'll put it all into meters here. So it says D is 0.5 millimeters. Okay. So 0.500 millimeters is times 10 to the minus 3 meters. And it says the ninth order dark band was located on both sides of the center by that amount. Okay, so if you're looking at the down on the experiment, you have the central maximum, and you have 1, 2, 3, 4, 5, 6, 7, 8, way out here, number 9, and then you have the same sort of pattern kind of going to the other side. And so they're looking way down in this region right here, and they're looking at This is the first dark band. Here's the second dark band, the third, the fourth, the fifth, the sixth, the seventh, the eighth, the ninth. So they're looking at this right here is where they're making their measurements here. Okay. And that distance from the central maximum to that spot is this 4.4631 millimeters, so times 10 to the minus 3 meters. And in this case, L is 40 centimeters. Okay. So I think I'll just put that down as that many meters. And we're going to look for the wavelength of light. And, what do I put in for M? So remember when you're counting dark spots, if you're looking straight onto this pattern, here's the central maximum. And then when you come over here and you have the first bright fringe, and over here you've got the first bright fringe. This is the first dark region. That's the first dark band, but it's M equals 0. So if you go to the ninth one, I think you need to put in an eighth here, right? So the ninth dark band is labeled with an 8. So the first dark band is M equals 0. This is the second dark region, and that one gets M equals 1, right? So they're off by one number when you're counting the dark spots here. So the ninth dark band is going to have to be equals M equals 8. And that's what you're going to solve here. So once again, I think the hard part is kind of the words and how things get labeled here, but the math shouldn't be any big deal now. It's just a matter between you and your calculator. So let me try that. 4.4631 times 10 to the minus 3 divided by 0.4 divided by 8.5. And I get 656.338, blah, 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 nanometers equals the wavelength of light. And so, if I just take it to so many sig figs, the experiment tells me that the wavelength of light is 656.3 nanometers. And the known number is that out to 4 significant figures. So we almost don't see anything in terms of this approximation showing up as being a problem, right? So really all you've got to do is get a piece of aluminum foil and be able to cut 2 little slits into it and precisely know that distance between them. And so you can just get a machinist to make a very, very narrow piece of metal and put your X-Acto blade right on both sides of that and just cut little slits. You control D, and everything else is just a ruler. You can measure from slits to the wall with a ruler. You can see the pattern on the wall. You can just measure those distances with a ruler. So with just a 29-cent ruler from Walmart, you can be measuring wavelengths of light that you and I see. This is the first way that people really knew how to do this, until you start being able to make things that have a lot of power. Right? In the 1800s, you start then having batteries, and then you're able to understand electromagnetic induction, and you're able to create big enough currents. If you can make big enough currents, then you can start making machinery. And so you need machinery to be able to make precision lathes and stuff like that, to be able to mill out work, to be able to do experimentation with precision here. Then you'd be able to make a spectrometer and be able to make some sort of circular disc and be able to etch it precisely from 0 to 360 and be able to do this with the vernier calibrations on it so that you can get to within fractions of a degree. So until you can do all of that, this just needs a ruler, and we see really no error here whatsoever. So what you really need to do here is to really think through this idea of the path difference. The path difference between the two rays that are hitting the wall, one is typically longer than the other, unless you're talking about exactly the spot in the middle. That's the central maximum. And if the longer path can hold a whole number of waves, then the waves are back into sync and they're doing the same thing at the same spot, and you've got constructive interference. If, however, the longer path is a half of a wave, or 1.5 waves, or 2.5 waves, as long as there's a half a wave difference between the long path and the short path, then the two waves are out of sync. One is going up, the other is coming down, they're hitting the same spot, and now you've got a region of destructive interference. And that's all that's really happening here. So Young's double slit experiment, being able to measure wavelengths of light a little bit more than 200 years ago, is a tremendous feat, right? If we had Nobel Prizes back then, he'd be winning a Nobel Prize for showing that light has wave-like properties, right? Here we're measuring the wavelength. And because you get the interference pattern, that's a wave property. It's the interference of waves. Waves are on top of each other in the same spot at the same time, and sometimes they add together, and sometimes they subtract out. They subtract out, we see no light with our eyes. They add together, we see bright spots. And so this is pretty tough to reconcile, with something like a particle picture of light. So light behaving like waves, now looks like, okay, we see it reflect, waves do that. We see it refract, waves do that. We see it interfere, and waves do that. And a lot of this falls out of Huygens' principle, which is a wave principle. And so we're seeing, light behaving more and more and more, exactly like all waves happen to be behaving. In the next lecture, we'll take a look at the idea of probably dispersion, probably single slit diffraction, and then we'll look at the idea of polarization. And once more, we're going to be seeing that light is behaving like a wave. Every property we can find that waves follow, we can show that light follows that same property. Okay, so very nice. So hopefully this gives you some idea of what's taking place in part of chapter 24. Once again, the math here isn't hard. You just have to conceptually understand what it means by the path difference. And there are some little math tricks in there because we didn't have ways 200 years ago to measure these angles until you can make these precision protractors. And so, like I said, there's a few math tricks in there, but nothing that's terrible or anything like that at all. So hopefully this gets you going, and I'll see you soon. And so we'll take a look at some more of these properties here in chapter 24. Okay, so I'll see you soon.